Okay, this is a pre-taped lecture 23 for the class on April 9th and 12th, the advanced cadence layout of analog IC. So let's start from the handout. In last lecture, we learned how to lay out NMOS transistor and PMOS transistor. So here we are talking about more practical case and the advanced layout. The first technique we are going to learn is a multi-finger layout. So multi-finger layout means if we normally actually for analog IC we have large transistor, especially the width is large. So if we lay out a transistor according to what we learned in our last lecture, actually we will have very wide transistors, and that can lead to awkward layout and significant series gate resistance. Talking about the series gate resistance, we actually learned this in the noise section. The thermal noise of transistors consists of the In square equals to 4kT 2/3 times Gm. That is the noise current of the channel. And also we were told that there is another source of thermal noise in the transistor, that is the resistance related to my gate. Remember that the red area is a gate of the transistor, and this is built by polysilicon, which has a relatively high resistance compared to metal. So we have large resistance, especially when W is large, then the distance for the current to flow through the gate into the transistor is large. So we have a large Gm. An alternative we can have to lay out the transistor is to use multi-finger layout. So here on plot B, we actually divided the transistor into two transistors put in parallel. And in this case, we have two drains and one source, because the two transistors in parallel shares the source. So now each transistor has a gate resistance of Rg over 2, because now the length is reduced to half. Moreover, we are actually putting the two transistors in parallel, so the gate resistance is now this Rg over 2 in parallel with the other Rg over 2, so the total resistance is approximately 1/4 of the original Rg. That will greatly reduce the noise produced by gate resistance. And from schematic, let me show you the equivalence. So we have the first technique, multi-fingered layout, where originally we have a non-transistor. This is our gate, and this is source and drain. Now we use two fingers for this transistor. So gate of the first transistor, gate of the second transistor, and the source here shared. And when we use the multi-finger layout, we have to make connection in this way. Connect the gate together so that they are in parallel, and also connect the drain together. So now this is my gate of the whole thing, and this is a drain of my whole thing, and this is my source. And from circuit schematics, okay, before that, let me label the width of the transistor. This is a width, original width, W, and now the new width is W over 2. And on the schematic, originally we have this transistor with W as a width. And now we are dividing the transistor into two. Each transistor has a width of W over 2. And we put the two transistors in parallel so that they are equivalent to a single transistor with width of W. So to put them in parallel, this is my source and this is my drain. And here we have the gate. Okay, and the advantage is we make the layout looks better and we reduce the gate resistance. So advantage is compact layout. Moreover, we have reduced gate resistance. And in this example, we reduce the gate resistance from Rg to a quarter of Rg. However, here we ignored the contact. So if we have to analyze it in a more accurate way, you have to also consider the contact that connect your, for example, for the gate, connect the polysilicon to metal 1 and maybe further to metal 2 and metal 3. Those contacts also introduce resistance and noise. Okay, so this is the first point, multi-finger layout. And the second point, we want to analyze how to lay out a differential pair. And here we have the basic differential pair layout. On this layout, we have two transistors. And the two transistors are oriented in the same way, so the current flows from drain to source. Both transistors have the same direction of current flow. That is good. Helps the matching issue. But a not so good thing is this layout is sensitive to cross-chip gradient. It means actually when the two transistors are fabricated on a wafer, the temperature and the doping concentration at this side may be different from temperature and doping concentration on the other side. So cross-chip gradients actually describes the variation on the temperature and the process at different locations of the wafer. Different locations on the wafer. On the wafer. Okay. And another alternative differential pair layout is to make the layout more compact, not that wide. So we share the source because the source of the two transistors are connected together. So we share the source, and we have drain here, and two gates, one on the top and one on the bottom. So, and this is the top view. So the current for the first transistor flows this way. The current for the other transistor flows in an opposite direction, and that is bad. And that introduces extra mismatch. So those are the basic layout. And the technique we are going to learn right now is a common centroid layout that helps the matching purpose. The idea is simple. If we can put the two transistors at the same location, on the wafer. Then we almost have no mismatch between the two transistors due to the cross-chip gradients. And what we can do is we can apply the multi-fingered layout concept. We can divide each transistor into two. Like here, we divide transistor D1 into two, and the first part is put here, the second part is put on the other corner, at the other corner. So now the centroid of the transistor is right at this point. Same thing we can apply to transistor D2. We divide it into two and put one here, another here. And now the centroid for D2 is at the same location of this place. So in this way, we effectively have put two transistors at the same location, at least for the centroid, on the wafer, and this makes good matching. And actually, this can achieve the best matching performance possible. And because note that the two transistors shares the same source, so another thing we can do is we flip the bottom two transistors to flip the source to the upside and the drain to the bottom side. In that way, we have all the sources put together, and now we can share the source. So in layout, we can connect all the sources together, and now connect the drain of transistor 1 like this, and the drain of transistor 2 like this. And finally, we have this common centroid layout with multi-fingered gates. That is because, as we have said, normally the width of analog IC is very large, so we can further divide the transistor into multiple fingers. Like in this case, we divided transistor D1 into 4 fingers, 1, 2, 3, 4. And their centroid is still at its point. And we divide transistor D2 into 4 devices, 1, 2, 3, 4. And their centroid is also this point. So this is what we can practically do when we lay out a differential pair. Shown here is one option of the common centroid layout with multi-fingered gates, and we have another option that we rotate this part by 90 degrees and also rotate the other part by 90 degrees. So essentially, we can rotate everything by 90 degrees to get another layout. So let me show you on this blackboard, the whiteboard, the multi-fingered common centroid layout. First layout we have on the handout is we have 2 active regions. Each side we have 4 transistors. And we have source, drain, source, drain, source, SD, SD, S. Okay. First of all, let's take care of our source. So because all the sources of the differential pair are connected together, so we can do this. Connect the source together. And then take care of the drain. And we know that those two fingers are for transistor number 1. Those two fingers are also for transistor number 1. So we have to connect the drain of transistor number 1 together. Yes, like this. And also connect the drain of transistor number 2 together. So what we can do is like this. And finally connect the gates together. So those two gates and those two gates are for transistor number 2. We connect them together. And those two gates are for transistor number 1. We can do it this way. Okay, so now we have an equivalent 2-transistor differential pair. And the second option we can have is to rotate everything by 90 degrees. So second option, we can have two active regions like this. And I have 4 fingers. And source, drain, source, drain, source, source, drain, source, drain, source. For the source, we connect them together. It's too close. Let me redo this. Connect source together. And for the drain, those two transistors are half of M1, and those two transistors are another half of M1. So I'll use green color to get a drain of M1. So this is a drain of M1. And the other drain of M2. And now for the gates. Those two gates should be connected. And those two gates should be connected. And oops. Those two gates should be connected. We can connect them like this. And this is a gate of transistor M1. We can also draw the gate for transistor M2. So those gates connected, and connect them like this. And this is a gate of M2. So in reality, when you lay it out, the part that is most sensitive to mismatch is the active region. So you have to make sure the active regions are perfectly matched according to the common centroid theory. And for the signal path, do your best to make them symmetrical, but it's impossible to get perfect symmetry in signal path. Otherwise, the circuit will be shorted together. So do your best, use different layers of metal to make those connections. So finally, by those two kind of layouts, we have the equivalence of a differential pair M1, M2, like this, and the active region, no, the gate width should be W over 4, W over 4, and here W over 4, if the width of the transistor is W, and if the width of the other transistor is W. So we divide the transistor into 4 and make this kind of connection to achieve perfect matching. Okay, that is the theory part, and next I'm going to use cadence and show you how to do the layout, the real layout of differential pair in cadence using the multi-fingered common centroid layout theory. Okay.